Okay, thank you very much. Nice to see you all again. So today I want to present this formula, which seems to be quite complicated, but I want to explain it in a lot of details and do examples to understand the formula. And so this formula relates. So let's start first of all what we had yesterday. So we had this spectral curve given by this data, which generates the omega GNs. And we had this other spectral curve just changing y and x, which should generate this omega GN check. And now the question is, how are these two omega GNs related? Is there a closed formula for that? And the answer is yes. And I want to present how the formula looks like. So just remember, this one had poles at the alpha i's, which were the ramification points of x. And this one had poles, yeah, thank you for the light, yeah, at beta j's, which were the ramification points of y, so for 2g plus n minus 2 greater than 0. Good. We had this yesterday, and relating these two differentials is not easy. So basically where this formula I want to present comes from. So the first, in my eyes, the most important work where this formula comes from was done by Boris Bitschkov, who is here today on this conference, and also Sergei Shadrin, who is also here together with Piotr Dunin-Barkowski and Maxim Kazarian. So they computed a functional relation relating some objects. And this was very complicated, this functional relation. So it took like, I don't know, 1 page in a paper at least to define this functional relation. So it was of a very complicated form. And I computed like the G 0 case where this G is 0 with another technique. And this other technique showed that there's like a simpler version of it. And then I simplified this whole complicated functional relation they had. And this is what I want to present and show you now. And this functional relation holds in free probability. So it gives you in free probability the relation between higher order free cumulants and the moments. But it can also give you some new insight in algebraic geometry, intersection numbers on the modular space of complex curves, etc. Good. Maybe one thing I wanted to mention before I start is I want to extend this list of examples from yesterday, because we talked here about Hurwitz numbers. So there's also a spectral curve which computes simple Hurwitz numbers, and I want just to write it down. So we have the Riemann sphere as the Riemann surface. X of z is equal to minus z plus log of z. Y of z is equal to log of z. And B was this dz1 dz2 over z1 minus z2 squared. And this example does not fit in the spectral curve I defined yesterday because we have logarithms. I talked yesterday about meromorphic things. But you can play this game of topological recursion also by allowing logarithms. So this is actually fine for this algorithm. And if you do that, the omega GNs, Z1 up to Zn, what do they generate? So we have here sum over K1 up to Kn greater 0, product I from 1 to n, Ki to the Ki plus 1, Ki factorial. What appears here is this Hodge class, where we take the product 1 over Ki psi I Gn. So this is the integral over this class where we take here the geometric series. This already appeared yesterday. And e to the ki xi dxi. So if we take this spectral curve, the coefficients here are computing this simple Hodge integrals on the moduli space of complex curves of genus G and n marked points, where we have here the G is the genus and here n is this one. So I thought this example would be quite interesting. Yeah? Yeah, that's right. In principle, you should like take here without the negative real line. Yeah, I'm working with dx and dy, and they are meromorphic, so this is fine. This is usually the thing which is important, that the derivative is meromorphic. But the formula I want to present here has some problems with logarithmic x's and y's. So there are some subtleties, but actually for this spectral curve, for this one it works, but for other ones, not really. So, yeah, this is what I wanted to write down now. So I fixed my notation. So right, xi. So notation, what I want to use for the rest of the talks. So I have this zi, which is local coordinate on the Riemann surface, and the x of zi is, I will write sometimes xi or xi of zi to emphasize that it depends on zi. So this is my notation. The same for the y's. I will write yi or yi of zi to be sometimes more precise. Okay, good. Other questions? Then this formula is also more conveniently written in this function's capital W, Gn, where I write x1 of z1 to be here more precise, xn of zn, which is somehow defined by omega gn z1 up to zn divided by all the x1s, z1s up to xn, zn. So where we just take like the function in front of all these differentials. Okay. Then the same for the check. So we have here y1, z1 up to yn of zn is omega gn check z1 up to zn divided by dy1 up to dyn zn. Okay, and furthermore, we put everything together in a formal power series, so Wn of its arguments is written in a formal expansion in h bar. First, I don't want to make that. G plus n minus 2 Wgn. And we sum over g from 0 to infinity. And we do the same with the checked version. Okay? Because it will be very convenient to write everything down with these functions. And another thing which I want to introduce is also the primitive of these W's or of these omegas, Gn, x1, z1 up to xn of zn, which is defined from some base point to z1. This base point is not important, at the end, so I can choose it to be the same. Omega Gn of C1 prime, let's say, up to Cn prime. So, just to be complete, the same for the y's and the checks. Should be clear. Omega G and check, and here we have some parameters we are integrating over. And we also put them together in a generating series in H bar. And then the same like for the checks. Okay, and the functional relation I want to present is written nicely for these functions W or phi's. And remember yesterday for phi 0, 1, this was used in this dilaton equation. Also another comment is that these functions here, the phi GNs, are appearing for quantum spectral curve. So there's a way of quantizing the spectral curve. And these are very important for the quantum spectral curve. They build like this perturbative wave function. If you're interested in that, we can talk about that later, but also Elba is an expert on that. She's here and can tell you something more about that. Okay, so we defined these two or four families of functions, and
yes, these are multivalue.
These are multivalue functions. So in X, they are multivalued, but this is just a convenient way to write it because in Z, they are meromorphic function. Because these are also meromorphic function. And the lowest order pole was like of second order, so you can integrate them.
If you are
Yeah, right. But this function at the end will not appear. So just derivatives of it will appear. But it's very convenient to define them, to write them down. But at the end, if we expand this H bar, etc., just derivatives of them will appear. Good. So now look at the example Gn equal to 0, 1. So we have, so just remember, omega 0, 1 was y dx. Omega 0, 1 check was x dy. We changed the row. Then we have w 0, 1 as defined there of x of z. We forget this dx is y of z. W 0, 1 check of y of z is x of z. Which means that if we insert this inside here, W 0, 1 of W 0, 1 check of y of z is equal to y of z. So these two functions are formal inverse functions to each other. The same, W 0, 1 check, W 0, 1 of x of z is x of z. Okay? So this is maybe an interesting observation, maybe not directly clear for people seeing this the first time. What is with the example of Gn is 0, 2? We had that omega G 0, 2 was this Bergman kernel, and also for the checked one. And maybe to be able to see the definition, we use this, insert the definition of W0, 0, 0, 2 and W check 0, 2. And it's easy to see then that you can bring just the dy's to the other side and that we can write W0, 2 of x1, x2. Now the shorthand notation is given by dy1, dx1, which both depend on the same z. Just maybe to emphasize it here again. dy2 of z2, dx2 of z2, w0 to check of y1, z1, and y2, z2. And this is related, this functional relation, this relation between this function and this function, to the second order free cumulant relation between, if you want to see this as generating function of second order free moments and free cumulant, sorry, and second order moments. What do you mean on the right hand side? Yeah. So W02 is equal to. It's a prod. Sorry. Good. Now it's getting maybe. Yeah. Okay. I just leave it here. So, and what is now the relation for all Gn? So the disk topology is just the inverse function. The second order, the cylinder topology is just this functional relation. And how is it for all G and N? And it's, of course, more complicated. And the relation is written in terms of certain graphs. So I think at this conference there are a lot of different graphs, and now I try to define more graphs. So actually the graphs I will define are in principle hypergraphs, but so for those who know hypergraphs, which have hyper edges, etc., you should think of the hypergraphs, but I write them as bicolored graphs. So the definition of the graphs, so let this telegraphical Gn be the set of connected bicolored graphs gamma with n, so we have here Gn, with n circle vertices and some number of bullet, so filled vertices, such that the following holds. So the circle vertices are labeled from 1 to n. Then I want to say black, but it's white here on the board. The bullet vertices are just, so essentially bullet and circle vertices are just connected to each other. Yeah, so which means bicolored essentially. And circle vertices are just connected. And this bullet vertices have valence greater or equal to 2. And yeah, let's do a little bit more. We say also for a graph gamma in Gn, let Ri of gamma be the valence of the ith round vertex. Then also we associate a set I. You're only connected. Yeah, it's but I want to be precise here that So we associate a set I to which is a subset 1 to n to a bullet vertex which remembers to which circle vertex this bullet vertex is connected. So which is like this set of labels of the circle vertices connected to the black one. Okay, and this I of gamma is the set of all I. So let's do examples. Maybe last comment, there's the notion of an automorphism of these graphs, which preserves the structure, preserves these labelings, and swaps the edges. So that's right, but we can have loops, etc. So this set Gn is not finite; it's an infinite set. But if we restrict to like a Betti number, we heard it yesterday, to a number of loops, then it's a finite set. And if we look at the first examples, and we also associate the set I to the black vertices, etc. So G1 starts just with this circle vertex, which is labeled by 1. If we go to the next loop order, we have this circle vertex, which is connected to one black vertex through 2 edges. Then we can have at the genus 2 case would be something like this. Okay, etc., etc. Then what else do we have here in the definition? The set I would be, in this case, I is the set 1, 1. Here it's the set 1, 1, 1. Here 1, 1, and here the same like I prime. Okay, good. Then G2 starts with this graph, 1, 2. Here the set I is 1, 2. Maybe I should also mention, like here the automorphisms of this graph is 2. There are 2 automorphisms, the trivial one and the other one swapping these 2. These 2 edges. Here out is 3 factorial. Here out is 2 factorial times 2 factorial times 2, which is 8. Yeah, it's a multi-set. It's like the power set. It's a power set. We heard it yesterday also.
Remember the labeling.
Yeah. And then at genus 1, we have this graph, for instance. Then we have also This graph here's 1, 2. What else? Also, this loop can be on the other side. And also there's this multi-edge, where we have here 1 and 2, and we have this trivalent vertex, this trivalent bullet vertex appearing now here, etc., etc. So here, for instance, it's the set I as 1, 1, 2. Okay, good. So, and maybe also just write down the trees of G3, which are 1, 2, 3. And here 1, 2, 3. And also 2 further graphs of this type. Okay, good. This would be like the trees, and then we have higher genus, etc., etc. Well, here you mean? Yeah? They are not labeled. So this is not an ordered set. Yeah, okay. But I view them as a non-label. So, I mean, later I will have functions which are symmetric under these labelings. So this is not important. Okay, good. Then it's maybe also clear that we have a very nice subset of these graphs if we just allow the bullet vertices to have just valence 2, which reduces the number of graphs to a very small subset. And this appears later in the functional relation for cases where this omega gn check is 0 for all 2g plus n minus 2 greater than 0. So this is later maybe a nice example I want to show. But now we have to put some weights on these graphs. So we define the weight in the following way. Let the function s of t, let's say, be e to the t over 2 minus e to the minus t over 2 over 2. This is as a formal expression. This is like, we don't want to consider the analytic function, but just like the formal expression of it, which is the sum from n to infinity, x squared over, what is it, 2 to the 2n plus 1 factorial. Okay, maybe some people from Hurwitz's theory know this function. It appears in Hurwitz's theory. It's not a surprise. But we will need this function. And we define now for g and gn and I in this set I of gamma, in this set of subsets of this labelings to a black vertex. And let's write I more explicitly, I1 up to some ik. Sorry? Yeah, sure. Yeah, that's right. Sorry. Yeah. You're completely right. Sorry for the... Yeah. So then we define the weight. Yeah, it's on LaTeX var pi, but okay, the symbol here. Depending on the set I, h bar, and some additional parameters, u1, I1 up to uik. So I collect them just in a ui to be the product over all these elements I, j, and I of h bar u I j. This function s of h bar u I j. The partial derivative, since it's a formal power series, ij. Oh, sorry. I want to do it for the y's, y, ij. On the w check I of the set yi. And then we need some small correction. If the set has just two elements and these two elements I1 and I2 are equal, then we want to subtract here I1 minus yi2 squared at yi1 is equal to yi2. Because this one has also a double pole on this diagonal, so we can subtract it, and this limit makes sense. And furthermore, so we have here the set of yi1s up to yik's, and these objects here act on this function argument-wise. So there might be the case where two of or several of these elements in the set are equal, and how I write it here means that the first one acts on the first argument, the second one on the second argument, even though some of these elements might be coincide. So, and this is okay because we have this formal expression, but what we can do, so this S function was defined by this exponential to some power. So we have here this product. And if we write it out, we have e to the h bar ui dy over 2 minus e to the h bar minus ui dy I over 2 over let's write formula. So this is my abbreviation for this partial derivative. Let's write, we divide by a derivative. Don't show that to an undergraduate student, please. And since we work here with formal expressions in h bar, dividing by a derivative is nothing else than taking the integral formally. So in the integral of this w's was nothing else as I have defined here this phi's. This is why I want to have them. So we have here like this phi and check of yi minus the integral of this, which is essentially the logarithm, but if you have a higher genus spectral curve, it can be more complicated, but let's think of a genus 1 spectral, genus 0 spectral curve at the moment, where we just get here the logarithm. Add y I1 to y I2. And what also people, of course, know that if we have the exponential of a derivative of some formal expression, let's say we have e to the a partial derivative with respect to, let's say, x, some f of x, it's nothing else than a shift f of a plus x. So what these objects do, they just shift formally these phi's. So we can write this also like as a sum of, okay, I want to introduce here some kind of epsilon I j's, which are either -1 or 1. And we have here this phi check on n is wrong. It should be I. Sorry. Set I, and then we have like y, 1, 1, plus one of these epsilon 1s, ui1 h bar over 2, up to yik plus epsilon I k ui k h bar over 2. And we have a global sign depending on the epsilon i's, which are epsilon I equal to -1. So the first example would be something like phi1 of y plus u h bar over 2 minus phi1 of y minus u h bar over 2. And if you think of this as a formal expansion in h bar, the first term is the derivative which comes out, and which is again this w's. And the second one, the second example, if we have I is 2 or has 2 elements, we have y1 plus. So essentially what we find, we have this, so the check function here. We have essentially the signs plus plus, minus, minus plus, minus, plus minus, plus, plus plus, minus minus. You're right. And this continues like for all sets of I.
This kind of translation the variables, that means parameters. In order,
Yeah.
you need to have sense of this kind of expression.
Yeah.
But the contributions are convergent, or convergent functions to the condition of
At each order and h bar.
at each
Yeah.
bar, these are really functions, so
Yeah.
you can evaluate a different point.
Yeah. So, but just, I don't know, just looking at this expression, I thought it's very interesting to think of it as looking at some kind of discontinuity at some point, because this gives you like the difference from, I don't know, the upper half space and the lower half space. But these are not analytic functions in h bar or something like that in this variable. But this is like a nice way maybe to look at it from my point of view. So just to summarize again, we associate this quite complicated weight to one of these sets I, which is here. So we associate essentially this complicated weight here, check, to any of these black vertices, or this bullet vertices, not black, white. Okay. And then the functional relation needs this, this weight. And let's write it down maybe on the other board. So then what I called the simple, yeah? Oh yeah, sorry, yeah, this is maybe important. Okay, no, I will not. No, I will not read it anymore. Okay, there's. So the simple version of this functional relation, which was then proven by Sergey and Boris and Alexander Alexandrov, Maxim Kazadrian, Pyotr Dunin-Bakovsky, to hold for any meromorphic x and y's, is of the following form. So they proved that it satisfies the linear and quadratic loop equation topological recursion and have this projection property. So this is essentially the thing you have to do, but this is quite technical. But for the simple functional relation, which first appeared in my paper, but then proved by them to hold for any meromorphic x and y's, is of the following form, that we have w gn of x1 to xn, which is given by the h bar 2g plus n minus 2 coefficient of the following expression. We have a sum over all this set of graphs. We take the automorphism group, divide by them, and we take here a huge sum over all m1 up to mn, going from 0 to infinity. We have a product over all variables I from 1 to n of the following expression, e over dxi to the power mi, where we sum over, of something, which will come here, where we take the coefficient of the ui to the, so we take the ui to the power m coefficient of the rest of, first of all, here this dy of dxi appears again, which was already there. And then we have also the exponential of, oh my God, this is a very long formula, yi plus h bar ui over 2 minus check yi minus h bar ui over 2 minus xi ui, so this is also in the exponential, times the product over all these sets of labelings for bullet vertex in this set I of gamma of this weight I h bar ui. So this is the formula. I mean, it's complicated. I hope you're not afraid to look at it or to try to compute something with it. But this is the formula relating the W checks, which are inside this phi's. Okay, no. So there's maybe also part of the definition of this phi's. And these weights, which are also defined through this y's. But, I mean, we can look at examples of this formula. So this is like, you have this huge expression here on the right-hand side. You expand formally in h bar. Therefore, also, this is a formal expansion in the ui's. You take the ui to the mth coefficient, and of this thing, you have to take the mth derivative with respect to x, and you sum over all the graphs. What property should have this formula? So we know that the W check GNs appearing here, and also W G1 appearing here, have poles just at the ramification points of y. On the left-hand side, we should have poles just at the ramification points of x. So all these poles should be cancelled through this formula. So one can maybe imagine a little bit. So this would give you like a 0 at the ramification point of y. This generates a ramification point of x, which we want to have. And this formula does it. So this is one of the consistencies checks you can do for this formula. On the other hand, we have appearing here something of the form W check 0, 2 of y1, y2, if we have like such kind of part in these graphs where we have here maybe 1 and here 2. And this object has a pole on the diagonal. If so this is like of z1 and of z2. If z1 is equal to z2, this would generate a pole on the diagonal. But if we sum over all the graphs, all these poles on the diagonal should cancel through this formula at each order in h bar. And this is the case. So whenever you have such kind of term, such kind of graph appearing, this should generate a pole on the diagonal if z1 is equal to z2. But on the left-hand side, we don't have these poles. So through the summation of all these graphs, this pole should be cancelled. So, good. Let's look at an example of this formula. Yeah? You take the difference and expand in h bar, and then like the leading order term appears, and then just derivatives of this phi survives, which are these w's. And these w's in the variable of z are meromorphic functions. Yeah, but phi 1, so this object here, the leading order term is w1. So if you expand, if you put h bar 0 here and 0 here, the leading order term is 0, and then the first term which appears is the derivative of this object.
Because you take the difference.
Yeah, because you take the difference all over. I mean, yeah, because also there we take, I mean this formulation over there, we take like the difference in every variable. And good. So, yeah, it's like a horrible formula, but the thing is, it is a very universal thing. So it relates for any spectral curve, x and y, this generated WGN checks to the WGNs. And in one or in some examples I mentioned before, I said to you that the WGN checks are 0 for all 2G plus n minus 2. So this is an example where this formula is much easier. This example appears for psi class integrals, for the intersection number of psi classes, for this Hodge integrals, and also for other examples. So this is a very interesting set of examples you can imagine. And okay, let's look first of all at the following example. What happens if we have G equals 0? Maybe I should also mention the following. So this set Gn is an infinite set, but if we restrict to a fixed genus here, in this set just graphs contribute which have the Betti number G or less. So this is like also one important thing here. So we don't have here an infinite set of infinitely many graphs, because we take here the h bar to the 2G plus n minus 2 coefficient. This gives us the fact that we just take graphs up to this, up to the Betti number, or up to the loop number G. Okay? What happens if we have G equal to 0? So, maybe the most important example. So, S of t, the function is 1 plus something, and we just need the first order. Then this exponential of the phi 1 check, etc., etc. So the leading order term generated here in the h bar expansion is cancelled by this term. So the whole exponential as an expansion in h bar is 1 plus h bar squared something. So the exponential is 1 plus something of order h bar squared. Here also the rest of h bar squared. So for genus 0 we have this. Then all the automorphisms trivial. These weights are the following, where we have here the u i's, w check 0, I, y I, plus something of higher order in h bar, which is like 2i. Okay? And so the functional relation is then given by the set I, so no, sorry, x1 up to xn, where we take here just the sum over, let's say, the trees in the set of graphs, which is a subset of the set of graphs. So we just take the trees because this is verified by this h bar expansion and just taking this coefficient. And then here we have again this product, I equal 1 to n, minus the derivative of the xi's. And it turns out this summation over the mi's and taking exactly this coefficient here is related to taking this coefficient here, reduces in this case to the valence of the ith vertex. So maybe we should draw a picture. Yeah, we have this picture here. So for instance, if n is equal to 3, we have here, this object has valence 2, and all these ones have valence 1. And we take here the derivative of the valence of the ith round vertex, minus 1. Then we have all these products, dy I over dxi. And here, a product of the set I over of check 0 I y I. So this is the genus 0 example. So if we take now an example of this example, so what can I erase? Maybe that. Oh, how long? Oh, just 5 minutes. Oh man. So now we take Gn equal to 0, 3. So for 0, 3, we just have these graphs here and two further where we have either a 2 or a 3 here as a central vertex. So we have essentially 4 terms. W, 0, 3 of x1 up to x3 is given by the first graph, where all the valencies of the vertices are just 1. This was this first graph here. So this gives us, so this does not appear. We have here this product. So we have dy1 over dx1 up to dy3 over dx3 of w check 3 x y1 up to y3 plus we take the first derivative. We take now the second graph there. We need to take the first derivative with respect to x1 of this product we had here again. Oh, 3 of w check 0, 2 of x y1, y2, check 0, 2, y1, y3, plus the other two terms were 1 and 2 is interchanged and 1 and 3 is interchanged, so the same one. So we have no derivative is acting here, so we have like the same topologically the same correlation function appearing here and here. We just multiply it by this differentials, and then we have to take the first derivative if we have several appearing there, where one of them comes from here and one of them are coming from this black vertex. And then we have two other graphs, which gives you other terms. Okay, good. And this holds to any genus, to any number of marked points. Good. And I also give you another example. What happens if we have Gn equal to 1, 1? So we have to expand everything to the next order in h bar. So the exponential will now contribute. Also, we have here, so the graphs which contribute are just the circle, just this graph where we have this circle vertex, this one, and I think that's it, yeah? So these two graphs contribute, and we have W1, 1 of x, so x of z, is then given by minus dy over dx, 1 check of y of z. Plus, let's write first this term, 24 d over dx squared of this dy over dx, and then we take here the second derivative with respect to y of the function x, plus, I will explain where it comes from. Where we take here the 0, 2 of y, where this is like this. We take here, I mean, we had to subtract this term there above to make the diagonal well defined, which is exactly what appears here. So I write it as a tilde. And this term here, which is now new, which does not appear in for trees, which comes from the expansion of the exponential up to the next order, this phi 1 check minus phi 1 check, which expand at the next order. And this factor 1 over 24 is on the one hand like the psi class if you integrate. I mean, this is related to 1 over 24, and which appears here through this expansion of this function s. So if you look at the coefficients of this expansion s, the first factor is 1 over 24, and then you have like higher derivatives acting here. So if you have something of higher genus, no, it does not come from the symmetry factor. The symmetry factor, so it comes from this graph, which is just the circle vertex. The circle vertex has no symmetry factor. So it comes from the expansion of S. So S of t goes like 1 plus t squared over 24 plus etc. And this is, so yeah, if you have something of higher genus, so you have contribution like of the same topology, but also of less topology, but therefore of higher derivatives. It's quite complicated, but what can we do now? We can, I mean, this is what I want to talk the next time. So either I give you like a more refined version of this formula, but I don't think I have enough time for that. But we can apply this formula. So we have this spectral curve where we know that it generates psi classes or lambda, this Hodge classes, intersection numbers, or other things. We can just plug it in here and find new formulas for these numbers. Or this formula also captures like the the relation between higher order free cumulants and moments, but it's quite involved. And maybe I want to emphasize again that this is like the most canonical version of this formula. Before it was like even more complicated, I would say. Okay, and I think I will stop here and yeah, thanks.